Okay, so this is a worked example of estimation of return period for annual maximum floods, or indeed for rainfall events at any measurement station. It's taken from the book by Purcell, Design of Water Resource Systems, which is available on reading lists at Liverpool. It's an electronic book, so you can download all the chapters in this book and look through and work through these examples yourself. The basis for this procedure is the analysis of a long time series dataset for either flow or indeed for rainfall at any particular monitoring station. In this case, we're using the River Suir at Newbridge in Ireland, and this is a dataset which looks at the annual maximum flow in any year or in every year between 1955 and 1983. Again for the River Suir at Newbridge. And the example is asking us to process this series using a probability function, the Weibull or the modified Weibull probability function, so that we can obtain a graph of flood flow against return period. And so this is what we do in order to try and estimate the return time for floods of a given flow intensity, so that we can design our water resource engineering to an appropriate return period. So this is looking at the design storm or the design flood, which we want to protect our engineering structure against. Okay, so we have a set of data. We have the year in the top row, and then we have the flow data in the second row there. And of course, in every year there's significant variability between from year to year. So the first thing to do with these data is to rank them in descending order. I very briefly mentioned this in the classing unit 2. But so this has just taken that data set, and instead of the years along the top here, we put rank through from 1 to 28, and then we've taken those flow data, we've ranked them in descending order. So number 1 is the highest flow, right down to number 28, the lowest flow. So this is the maximum flow observed in any particular year, and it could equally be the maximum rainfall intensity measured for any given year. So once we have those flows in a ranked order, we can then estimate the probability of exceedance for each flow. So this is the probability that we will get a storm with a flow rate or rainfall intensity higher than any given entry in this sequence. So the method is worked through here. So we take the lowest flow, which is 63.5, and then we see that of our data set, 27 of the 28 possible flows are clearly greater than this, because this is the lowest one. So all of these ones exceed that flow. So the initial estimate of the probability of exceedance is 27 over 28. So there's a very high probability that in any year we're going to exceed this flow based on this data set. And so this is the basis for the Weibull formula, where the probability equals the rank of any given entry in a data set divided by the total number of the flows plus 1. But statistical theory will tell us that this simple formula is not satisfactory, because we don't know the total population. This is only 28 years out of clearly a very large number of potential years. And so we can update that formula a little bit. And Gringorten did that in 1963. And so we use this modified version of the Weibull formula. So it's essentially the same form, but with differences in the weighting given to each, the rank or the total. to get a statistically better accuracy in terms of the probability of exceedance. So we apply this formula to this data set here. The easiest way of doing that is to draw up another table. So here we've reordered it slightly. We've got the flows down here from the highest to the lowest. And we have the ranking position from highest to lowest. And this allows us to calculate the value of P, the probability of exceedance. Here. So these are the values calculated from this simple formula. And then we've got one more column here, which is the return time. So we saw in the class notes that the return time, return period, is the inverse of the probability of exceedance. We just take this value of P for any given flow rate, and we take 1 over P to give us the value of the return time, T. Okay, and once we've done that, we can plot up the graph which they asked for, which was flood flow as a function of return period. And this is simply having calculated the return period T here. We're plotting that along the bottom line, and the flood flow from the first column along the y-axis. And we obtain this distinctive graph where you've got a sharp, almost logarithmic type of relationship between very short return period flows, and then this other relationship between return period and longer flows. So at short periods, the return time, the flood flow increases very greatly over a short number of return, over a short period of return time. But as you go beyond maybe 5 years, you then get very little difference in the peak flows for increasingly long return periods. And this reflects the frequency and the type, the style of rainfall responsible for storms here at short frequency return times, as opposed to very rare and insignificant events, not insignificant but infrequent events at higher return periods. Okay, so that's a simple process for taking a data set which you've obtained over a number of years from a measurement station, and using a simple probabilistic approach, simple statistical approach, to work out the probability and hence the return period for any given flow rate. So remember, we're looking at the probability here is the probability that in any 1 year the peak storm is going to generate a flow greater than the equivalent value here. So this is the basis for giving us return time estimation. Okay, so work through that example, and clearly you could look up on the National River Flow Archive, if you type that into Google and search for river flow data for any of the many river stations in the UK, you could obtain a similar data set to this one here and actually practice looking at the return time, return period estimation for any given site in the UK. So that might be worth having a look at if you're interested and you've got time. Okay.